books laid out. So if I ever wrote a calculus book, it would be done in this kind of way. Okay. So I'm showing you guys what I'm doing. And I have written manuals in my past, statistics manuals and math stuff. So, but anyway, so I do have some experience doing that. But I want to emphasize this important idea. Okay. I know this is, you say, oh, Mr. Judge, you're already talking about continuity. Yeah, and I'll show you why. We mentioned this thing yesterday, okay? I started to talk about it. What is continuity? It's a lot more technical than you realize. But here's what I want to say to you guys. Continuity, all right, definition. We say a function f is continuous at x equals a if the limit as x goes to a of f of x equals what? F of a. Okay? This is gold in a lot of ways here. Okay, so let's go with this. So I kind of want to leave you guys with a kind of a very important point over the weekend. This is a limit question on the left. This is x as approaches a for a function. So remember, a is a fixed value. Is that right? So, okay, a is fixed. And if it equals the value of the function, if the approach is equal to the value of the function at a, then we can say that this function is continuous at that location. So this is actually really kind of jumping ahead, but let me kind of remark to you guys why I care about that idea so much from the start. Because I want to now transition and give you this definition, because this is a way, in this context, this is a very good way to evaluate our what? Limits. So the only reason I'm talking about this is because on the left side here, you're asked to evaluate a limit. Okay, that's on the left side. What does that equal? To the value of the function at the point. Only when the function's continuous. Now, that means, technically, the limit as x goes to a from the left of the function must equal the limit as x goes to a from the right of the function, which equals to the value of the function and is that number, that finite number we called L. L is finite. So, ladies and gentlemen, there you go. That's something we want to work on today. And that's going to make a lot of things a lot easier for us in the long run, by the way. Your book kind of does this. Your book will call it direct substitution. Well, it's the same as continuity. So Stuart, who's a millionaire with his book, talks about that. Yes. Yep. And also, too, just so you guys know, like I said, I broadcast the lectures. I record them. They're in Canvas. So at any time, you guys are welcome to go back and take a look. I only do it because my students have told me it's very helpful. And some of you guys might be doing that. You go back and take a look. You'll be doing that stuff too. All right. So let me share with you guys some of the stuff that I do for fun. Not cleaning out the closets. But I was working yesterday, last night, looking over what I have, what I don't have. I created some new things. Okay? I'm always doing that, always. Your 261, we're looking at here the new Calculus 1 library. under limits and continuity, because I put it together. And I want to look at this one here. This is notes for limits of polynomial functions. So let me remind you guys, what in the world, we're going to look at it this way. I have it organized in my head for you guys and even on my website. We're going to start looking at the polynomial functions. We're going to keep it simple. Does anybody happen to know? What's the definition of a polynomial function? You guys seen polynomials where? Pre-calculus, right? So I defined it. It's sometimes defined this way in that setting. They use p of x. You could use what? F of x. It doesn't matter. It's a function. What's the definition? Do you guys remember? an x to the nth power plus an minus 1 x to the n minus 1 power plus dot 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 a1x plus a naught, where, what's the story? an minus 1, a1, and a naught, these are all what? Constants. Okay, so I want to kind of, let's find some emphasis. I don't know, let's try to use some pink or something. I don't know. Whatever. Those things are constants. X is your variable. Okay? N is called the degree of the polynomial. N is the degree. You guys remember that? From pre-calculus? So those polynomials are really nice. Polynomials are like your beautiful functions in a lot of ways. That's how I think of it in my mind. They're beautiful. And you say, well, what's so nice about them? If you look at the graphs of polynomials, what do you guys see? Right? I want you guys to note something and get that in your mind as well. These are beautiful graphs. Okay, they're like, in my mind, they're like rolling hills, okay? Think of rolling hills, beautiful rolling hills, nice curves. We'll talk about what that even means. Nice, beautiful, oh, nice and smooth curves is what we'll say. That's really a math term, by the way. Being smooth. You got nice, smooth curves, rolling hills. Probably one of the most important fact about polynomials we'll talk about, you're not supposed to know yet, but I'll tell you. They are continuous everywhere. What? They're continuous everywhere. Do you guys know what that phrase means? Here's what it means to be continuous everywhere for the whole real number line. That's what is so nice about polynomials. So keep this in mind, because I'm going to share with you guys some examples of polynomials, why we care. Well, I'm going to start with those. Then I'll go to some other nice, beautiful, smooth curves, sines and cosines. Those are nice and beautiful. You know, there's a lot of nice, beautiful curves that we'll look at. Polynomials are the first type, and then sines and cosines in the trig context are the second type. Okay, so you start kind of simple in a way, and let me show you what I mean by that. So I did spend some time. This is always a work in progress. And you go, okay, is this what you did last night? Yeah, I was kind of just fooling around. And, you know, we're looking at the limits of polynomial functions. And what's the key idea? Polynomials are continuous everywhere. That means for any a value, it's going to be continuous. And why is that nice? Because I could just simply use this definition here to evaluate a limit. So, and that's what they're going to ask us. They're going to want you to evaluate a limit. See, ladies and gentlemen, you don't always use the numerical approach. You don't always use that, what I showed you yesterday. You start there, and you let everybody know a limit is about an approach, and you're getting close and close and closer, but let's take a look here. This is my picture of continuity I worked on last night. Being continuous at the value A. Now, I want you guys to look at this picture, because what you see here is three things. You have the left-handed approach to A. Okay, all those values of x are approaching A from the left. Is that right? And you have the right-handed approach as well. If I could do that. So you're approaching from the right as well. They're both approaching the same location. Is that right? So really, this is a picture of the left-handed limit equal to the right-handed limit being the value L. And in red, that's a third thing to consider. This in red is the value of the function at A. So in green and in orange is the approach to A from the left or right. So notice I'm going back to a graphical approach now for you guys. And it's equal to the value of the function at A. This picture is what it means to be continuous at A. This picture right here. Now, to be continuous everywhere, hey, this is the picture. To be continuous everywhere means the same idea is happening for every single point on that curve. It's happening here, it's happening here, it's happening here, it's happening here. You know, you change the A value, that picture is happening everywhere on the curve for all real number values A. And then I want you guys to notice, isn't that kind of a smooth curve, meaning rolling hills maybe? See some rolling hills, some smooth curves. Not every graph has that look. Polynomials do. So that's why I start there. And here's an example. You may not believe it, but you might say, hey, Mr. Judge, I don't see any curves. That's just a line. Okay, well, that's right. That's true. There's no curves there. We call it a curve. It's a polynomial. But the degree of this polynomial is 1. Is that true? So the function is this. Here's your function. F of x is 3x plus what? 5. That's the value of the function. What do you know about this polynomial? It is what? Continuous everywhere, in particular at the value x equals 4 here. Okay? That's the fixed point. You're continuous at 4 because you're continuous everywhere. It's not just 4. You're continuous at 0, at -2, at 1, at 1/2, at pi, at e. You're continuous for any real number. So in this example, it is 4. Now, how do you use that knowledge and information? What you do is you use the definition I gave you. That the limit as x goes to a of f of x will equal f of a. This is what you guys use to evaluate the limit. Now, how simple is that? Well, let me show you guys. This will equal 3 times what? What's this a value? 4 plus what? 5. What you guys have over here on the right side to do is arithmetic. You guys have to follow order of operation. Please excuse my dear Aunt what? Sally. So every one of these questions on this worksheet, they're polynomials. All you guys got to do is arithmetic to evaluate the limit. You go, really? It's that simple? Mm-hmm. It's that simple. You go, okay, well, what do I mean by that? What do I do first with order of operation? Multiplication. Yeah, what's 3 times 4? So is this going to be 12 plus 5? Yeah. And what's 12 plus 5? You're done, ladies and gentlemen. That the value of that limit is going to be what? 17. Yes.
Can I talk to them about the 261?
Okay, come on in.
Sure. Can I turn on the lights?
If you like. I think we already had that discussion. You guys okay? Sure.
Okay.
Put on the lights. We're going to blind everybody.
Oh, no, sorry. All right. Good morning, everybody. My name is Mr. Castro. I'm the department chair. I'm here to talk to you about our supports that we have for Calculus 1 classes. Okay? Specifically, our 261L, which is our new course. Okay? So, first and foremost, you have the tutoring center, which is located right down the hall in 009. Tutoring center's there, Monday through Thursday from 9 to 7, Fridays from 9 to 4. So if you ever need tutoring, walk in, it's absolutely free. Give them your student ID number when you walk in. We log you in, grab a seat, get your stuff out, raise your hand when you have a question. Tutor will gladly help, okay? That's number 1. Number 2, I know you have an SI coach. Do you have your SI? Is your SI coach?
One more. Hey, like a dark, they told me. You want to go back to sleep?
You have the math. Thank you.
Okay, you guys. Now, let me ask you this question here. Like I said, and it's please excuse my dear Aunt what? Sally PEMDAS. That's order of operation. This is arithmetic, and this is why polynomial functions are amazing, because they're asking you to evaluate a what? Limit. You get to use functional evaluation is what I'm saying. And, you know, the author calls that direct substitution. It's continuity. Let's just tell you what it is. So I created a worksheet where you guys get to see. Now, take a look. This is the limit as x goes to 4, because I'm doing a transition as well, where that fixed value is actually 4. Is that true? So remember the left-handed limit approach. You start anywhere, and you approach 4 from the what? From the left. What that means is all these points are getting closer and closer to some point out here. The y-coordinate value is getting closer to that location on the curve, because every one of these points on the curve has an x and y coordinate. Is that right? And then on the other side, okay, you can start anywhere. You can even start at 5. Just get closer and closer to the number what? 4. And on the curve, it's a line. You're approaching the same exact location. Is that right? What's the location? Well, the x value is 4. And what's the y value? It's 17. So what I'm saying is the green and the orange are getting closer to the same y value, which is 17. And that's the limit answer. This is why we got 17 here. Now, it turns out the value of the function at 4 is 17, because what did we just get through saying about this situation? The function is continuous at 4. The left-handed approach to the limit equals the right-handed approach, which means the limit is going to be 17. It's also the value of the function. So I'm using, and I'll write it again, the limit as x goes to 4 of that function is equal to f of 4 because of that idea of being continuous at the location. You just get to plug in the value. And you say, well, what do I do that for? Well, you do that for polynomial functions. You just have to know what a polynomial function is. You have to recognize it when you see it. The good news is you had pre-calculus and you know what polynomials are. In fact, you probably had to graph them. Anybody remember graphing polynomials? There's a process. That's what I'm talking about. So, you know, the funny thing, like I said the other day, was what I teach you is like 10% new. The rest is 90% of what you already had. Yes.
Would L be 17?
Yeah. So in this thing, this is that limit value. And then the limit is finite, by the way. And you say, what's finite? It's a number, but whatever. Yes. We'll see something a little different later. But right now, the first day, hey, guess what? We're evaluating limits for what? Polynomial functions, and you get to see the curve, the graphical approach to it as well. We got numerical, we got graphical. Anyway. Okay, is this a polynomial? Say yes. F of x equals what? X minus 6. What's the degree? Okay, so that's going to equal negative 2 minus 6. What equals what? Negative 8. You evaluated the what? The limit. You just plugged in that value there. Okay, so at negative 2, it's the same situation. As we approach the fixed number, from the left, these x values are getting closer and closer. Okay, what's going on over here to the curve? You're getting closer and closer to a location. On the right, start anywhere. You can start at negative 1, get closer and closer. This is the x-axis, and you're getting closer and closer to a location as well. What's that location? Negative 2, negative 8. In other words, we might have to just put a sort of ghost line. Over here is going to be somewhere, it's going to be negative 8. That's where negative 8 is, okay? So this is our limit answer. So you guys can verify both graphically and what? Symbolically, I guess, in some way. The limit value is negative 8. That's your L value. Easy peasy lemon squeezy. You guys okay with that? You want to appreciate a good, easy day. Is that right? All right. Is this a polynomial function? It's polynomial? How do we know? What's the degree of that polynomial? Oh, and then there's a typo here. There's no such thing as negative 0. Sorry. I think I just changed it. I got to fix that. What's the function? F of x is x squared plus x minus 4. Okay, what do I have to do then to evaluate this limit? Plug in what number? 0 squared plus 0 minus 4. Do you guys know what that is by order of operation? It's negative 4. This is your answer. This is the limit value. This is your L. Easy peasy lemon what? Lemon squeezy. All righty. Now, is it true as we go to 0 from the left and the right? Could it be true? Start anywhere. For these x values, this is the x-axis. As I go to 0 from the left, and as I go to 0 from the right, notice I am approaching what y value? These are y values we're approaching. This is where what would be? Do you guys know what's going to be here?
-4.
It's -4. Yes. Could you guys see it on both the graph and numerically? That's what a limit is. What is nice is the picture I told you guys. This is a picture of being continuous at a point. The left-handed limit equals the right-handed limit is the value of the function. Now, I'm going to give you guys a little note here. I want you guys to know this as well. They could have asked you, what's the limit as x goes to 0 from the left of this function? X squared plus x minus 4. What if they asked you a left-handed limit question? See if you're awake. Does that change your answer? No. It's still what? -4. Aren't you approaching that y coordinate because this is the location, 0, -4. In green, aren't you approaching the -4 for the y coordinate value? Oops. Okay, you're approaching that? Yeah. Could I cite the fact that it's continuous? Yeah. But I just want to make sure you guys understand this because I know you just seen a little bit of it yesterday. They could even change this question and say, what's the right-handed limit approach? It's -4, essentially because we already know the definition of what does it mean for a limit to approach 0, irregardless of the approach. It means both the left and the right are the same answers. That's what it means. So they can throw that in there, and sometimes the book does that to you. And you can say, I can still handle it because it's a nice, beautiful what? Polynomial function. And these polynomials are, just again, look at the attributes of it. Nice, smooth curves.
Is that because it's approaching one axis and not the other?
No, it's approaching the same location.
Yeah, that's why.
That's all.
On the y-axis, right?
Well, it happens to be on the y-axis because that's where x is 0. It happens to be there. But like in this previous example, it wasn't on the y-axis. Okay? You were approaching -8 from the left and the right. And the answer is always going to be, you say, why this is a y value? Well, an L value. It's really the y coordinate is what we're saying. X is changing and you're answering what happens to y. That's the limit value. Yep.
So when you ask, like let's say on an exam, if it doesn't have the negative or positive, do you just?
It's both.
It's both.
It's both. And we'll see that.
Okay.
It's both. And that's a very good question. See, this question is really asking you what's the left-handed limit and the right-handed limit. Although you go, but it doesn't say that. You just have one. I know, but to answer a limit question, it's really answering the left and the right-handed approach. Okay. However, this is the most perfect situation you could ever ask for. Polynomial functions. So, I can change this on you and say, okay, what's the left-handed approach? I think we're using green, right? The fact that you're dealing with what? What kind of function is this? A beautiful polynomial. You're going to leave here going, polynomials are just beautiful. Not because what? Well, the graphs are nice, beautiful, smooth curves. Look at this. Isn't that beautiful and smooth? You guys know what I mean? When you graph these polynomials in 260, you were trying to draw beautiful, nice, smooth curves. Rolling hills. That's what I see is a rolling hill. Well, what are you guys free to do? You're free to use what to evaluate the limit? 4 times 1 cubed minus 2 times 1 squared plus 1 minus 7. You got to use order of operation. Please excuse my dear Aunt Sally. Okay, go to an L course. Ask them, can you review order of operation, please? Register for that 261 now. Order of operation, please. Go to the SI. Okay, order of operation. Go to tutoring. Order of operation. Okay. Do you see what I'm saying? Please excuse my dear Aunt Sally. What do you guys do first? 4 times 1 minus 2 times 1 plus 1 minus 7, which gives you 4 minus 2 plus 1 minus 7. Do your arithmetic left to right now because they all have the same priority. 4 minus 2 is 2 plus 1 is 3. 3 minus 7 is negative what? 4. But I didn't just write this for you guys to use arithmetic. Although on a test, if they say, please evaluate this limit, and you see a polynomial, you go, oh my God, Mr. Judge, God bless that man. I just use order of operation. I evaluated this. You do not have to graph this. You're not going back to 260 and go, how did I graph 4x cubed minus 2x squared plus x minus 7? You're not doing that. You're using order of operation. Now, you might say, but why did you put the graph? So, because you want to also see the graphical approach to a limit. You want to understand limits very thoroughly. So we're approaching the number 1 from the left. Is that right? So let's approach 1 from the left. Where is 1 at? It's here. If we approach these x values, start anywhere, going to 1, on that curve, what's going on? You're getting closer and closer and closer to what? This point, this location on the curve. It's a left-handed limit. Doesn't matter. That means when x is 1, what's that location? Negative 4. Okay, isn't that location? You guys see what I'm saying right here? Because polynomials are nice, smooth, continuous curves they're continuous everywhere. What does it mean to be continuous everywhere? All real numbers. In other words, I can change this on you. I'll give you another note. You go, Mr. Judge, what are you talking about? Well, limit x goes to 0 now. Let's say from the right, or just 0 period. The same function, 4x cubed minus 2x squared plus x minus 7. What are you free to do to evaluate this limit? Just plug in the value and then use arithmetic, order of operation. Please excuse my dear Aunt what? Sally. What's the limit value on this one now? It's negative 7. Your limit's negative 7. And I could now just look at this and say, what am I approaching now? What's the fixed value? 0? Okay, left-handed limit we've been doing on green. Maybe you say, I like just doing this here. All right. Right-handed limit, okay. Again, this happens to be on the axis. Doesn't have to be, though. What location am I getting close to? That's 0, comma, negative what?
4.
It's negative 7, right?
Yes.
Negative 5, negative 6, negative 7. The answer is always the y-coordinate value. You're approaching there. So it's the best situation ever, having polynomials. Polynomials are the best. Yes?
So we will be encountering poles or asymptotes within the parameters?
Not yet. That comes. I kind of feed you. How do you eat a steak? Anybody here eat a steak? One bite at a time. Here's in my mind. This is what I was writing yesterday. Even though I don't have to do that because I actually wrote things already before. But, sometimes you just, I don't know. Developing curriculum is my curse. It's a curse. It's actually a blessing and a curse. Is this here? So I was working on these notes here. If you look at the original notes I worked on, it has a video. I do have some of this, a lot of the details here, but I put it all together in one sheet. I'm separating the topics: limits, polynomial functions, limits for sines and cosines, limits for rational functions where you have vertical asymptotes, limits for the cotangent, tangent, secant. Those are rational functions, believe it or not. So I can probably put that in the rational function. Maybe I'll just combine it there. And then you got these other limits for, piecewise functions. I'm writing that one. Limits for what's called removable discontinuities. You see my point? So I'm giving you different notes and different examples of that stuff because it's fun to do, I guess. I don't know. But I also have it here, and I have it in the video here. I have videos of these things too, to the right there. So this class can be remote asynchronous if I wanted it to. But you might say, Mr. Judge, why don't you teach remote asynchronous? Does anybody want to ask me that question? Why don't I do it when I have the infrastructure? Because one thing you guys want to know is this. Your problem isn't getting by calculus 1. It's not your problem. Your problem is you got to finish a program. It's not finishing only one course. So they like to look at this, and I've argued with the state about it. Trust me, I'm notorious. When I speak, I get 3 standing ovations. Depends on who the audience is. Okay. The state and the RP group didn't give me a standard deviation. I mean, they don't want to hear what I have to say. But here's the thing. You have to get through a program. It's not getting through calculus 1. You put all this energy to get people through calculus 1, and then you got to worry about calculus 2, calculus 3, all the other classes. It's not just calculus 1. So what do you need? Knowledge and information. You got to master those skills. It's not just, your nightmare isn't over because you got through calculus 1. No, it's just begun. So you need legs, I say. You got to have strong legs to get through a program. So that's the idea. We got to get you through a program. And in some of those remote synchronous environments, funny things happen there. Those kids are hurting themselves. They're not going to be able to get through a program. In fact, some UCs, if they find out you took calculus 1 online, they're going to make you take it over at the UC. People don't know that yet. It's coming out. It's coming out. Ooh, I spoke to a colleague at Stanford University. I'm chair of curriculum for math in the district. That's one hat I wear. So it's coming down, and people don't know this stuff. And you go, where do all these kids signing up for remote asynchronous? And then even some of the instructors say, give me a remote asynchronous class. And I say, you guys don't know what you're doing, and you don't know what you're saying. What do you think happens when students transfer, or maybe they came down to a community college in the state here, they took remote asynchronous calculus and stuff? What do you think is going to happen eventually? They're going to make them retake that class because they know you're not going to have any legs to get through a what? A program. So it's not just one class you got to worry about. It's all your classes. Does that make any sense? What do you think? Do I make any sense to you in any way? I sometimes wonder that people don't understand a word I'm saying. No? Does that make sense? See, I'm going to tell you guys things I tell my own daughters, people who I love, my family. I'm not going to feed you anything different. That, I think, is messed up. Why wouldn't you tell your students the same things you tell the people you love? Why don't you? and some people don't. So that's it. It's nothing more. Okay? If Ashley was sitting here, Melinda's sitting here, Melinda, you're going to do that face-to-face class like your sister Ashley. You know, you're not going to do remote asynchronous. You're not going to try to do that kind of funny stuff because you need to have legs. You got to get through it. It's a program. That's the big picture. It's the program. So even though I can do it, I'll never do it. God help me. I better not say that, but never do that. I just won't, even though I have the infrastructure. And it'll be free. But so I'll sit at home. I'll work on curriculum because I believe it, because I think that this stuff is going to help you. So that's why I do it. I don't do it because I'm bored. I could do a lot of things. Take a look at this one. I gave you, I think, a very similar curve. Okay. It's different. But what did you guys learn today? What's the point? These are polynomial functions, and they're like the most easiest, beautiful functions you can work with. They're continuous everywhere. Just use functional evaluation to evaluate a limit. What's 2 to the 4th power? 16. 16 plus 2 plus 3. What does that give you? 21. You guys can look at the curve and see that as you approach 2 from the right, the y-coordinate should be 21. You go, really? Let's approach 2 from the right. Unless no, I got the wrong curve. Wrong curve. You know how I know? Right in here. Typo. See what happens? When you're the guinea pig? Got a typo. I must have punched in the wrong curve. So I punched in the wrong curve. How do I know? See here? That's 13. That's not 21. So if you approach from the left or the right, I know they approach the same location, the same y-coordinate, right? So I'm going to have to find out which the one that really is. Yeah, but whatever. We evaluated the limit. It's just that the curve is not consistent with the function. It's a different function. It might be the prior one here. Maybe I did a screwed up. Or maybe not. Who knows? All right. What about this? This is a nice... What kind of function is that? Is that a polynomial function? Okay. What's the limit then? They want you to go to what? -1 from the right. Okay. So you got 3 times -1 squared minus a -1 minus a 2. You guys okay with that? Because you have a polynomial function. They're continuous everywhere. They're continuous at -1. So do your arithmetic. Please excuse my dear Aunt Sally. 3 plus 1 minus 2. What is... Isn't this going to be 2? It's going to be 2. So as you approach -1 from the right, let's approach -1 from the right now, okay? These x values are getting closer and closer and closer to the fixed point of -1 on the right side. And what do you guys end up, where does that go as you go to -1? These are points on the curve. You're getting close to that location. Is that right? What's the address? Well, x is -1 and y is what? +2. Is that true? Is that right? You guys with me on that? Is that what we got over here? Yes. So this is the right picture is what I'm saying. Okay. So do you guys see how nice these curves are? The what? Polynomial curves. And then I have how many more examples? Okay, we're going to continue with working with limits for polynomial functions. Those polynomial functions are the easiest limits to work with. So this question is the limit as x goes to 0 from the left. So because the left-handed limit is the same as the right limit, they're the same values, the polynomial functions are continuous. Remember what we're using. The definition of what it really means to be continuous. That's the limit as x goes to a of some function is really f of a. It's functional evaluation. So like we discussed earlier, this would be 5 times 0 cubed now, plus 0 minus 6. And so you just simply use order of operation. Please excuse my dear Aunt Sally. So now you get 5 times 0 plus 0 minus 6. 5 times 0 is 0 plus 0 minus 6. So ladies and gentlemen, the answer is going to be simply negative 6. So I'll put the answer over here. This equals negative 6. Okay, so that the limit as x approaches 0 from the left, because this is a polynomial function, we just use functional evaluation. So this will be negative 6. Now let's take a look here. X is going to 0 from the left. Let's look at the graphical approach because we want to really understand the ideas behind this. So these are the x values. They're going to 0 from the left side. Okay, that's to the left of 0. Those are x values that are smaller than 0. On the curve, though, every x value has a corresponding y value. So as x goes to 0 and gets closer and closer to 0 from the left, we approach this point on the curve, which will be 0, negative 6. So it looks like every one of these dashed lines is a negative number. And the limit answer is always the y coordinate. That's your L, it's the y coordinate value. So sure enough, the graph is consistent with what we see. And let me emphasize again for those who might be needing to review that the function here is 5x cubed plus x minus 6 here. We did the order of operation already. We deduced the answer. So very often we just say, hey, just evaluate the function at 0, plug it in, and yes, we already know this equals negative 6. So we're just looking at this both in terms of the definition of being continuous and looking at the idea here graphically as well. So there's the details for number 7. We got this earlier today. Now, number 8. Another polynomial function. So, because it's a polynomial, this function is continuous for all real numbers. It's continuous for the x value being 1. So we can find the answer by using that definition here we just wrote down for you guys. Okay, so let me kind of bring it back down here just to be thorough. All right, you guys have that there? So we take 7 times 1 to the 4th power minus 4 times 1 to the 5th power. Okay, we're plugging in 1 into that function here. That's what they mean by just simply evaluate the function. And by order of operation, please excuse my dear Aunt Sally. Exponents go first, so it's 7 times 1 minus 4 times 1, which is 7 minus 4 equals a 3. Ladies and gentlemen, there's your limit answer. You evaluated a limit. And this is a two-sided limit because x is approaching 1. that implies we want to look at both the left-handed approach and the right-handed approach. So let's just verify the answer graphically. 1 is over here. So let's approach 1 from the left. Every point on that curve, ladies and gentlemen, is approaching this location here from the left. And then on the right side, x is approaching 1 from the right. It doesn't matter where we stop or start, I apologize. And then all those corresponding points, because for an x value, you get the corresponding y value. You're approaching the exact same location. That address, though, is 1, comma. Let's see what that is. This is 1, 2, and that's 3. So we're approaching 1, 3. And again, the limit answer is always the y coordinate value, or we call that a couple of things. That's L, that's Y, but that's the limit value. So that's what we're looking for on the curve. So sure enough, yes, the left-handed limit equals the right-handed limit. They're both 3. All right, good job. We got these polynomial functions that work out very beautifully. And look at the curve. It's nice and smooth, and it's nice rolling hills, a beautiful curve. We like those curves. All right, we're back to a linear, which is a straight line, but it's a polynomial. So since our function here is 6x plus 5, this is that function right in here. All we have to do is evaluate the function at the point -4, because polynomials are nice and continuous everywhere, which means polynomials are continuous for all real numbers. We just got to plug this in. 6 times -4 plus 5, which will give you -24 plus 5. And then that equals a -19. So, ladies and gentlemen, the limit is -19 as x goes to 4. And again, we got to check both directions graphically. And I apologize, x goes to -4 from the left. X goes to -4 from the right. So let's take a look here. And I guess we don't have that information. Shucks. Because -4 is really over here. And so we'd have to approach it. Doesn't look like the graph's there. And I'm not going to kind of get a new graph in there. But whatever. I think you guys have seen enough examples of this to understand what's happening both graphically and really in terms of the arithmetic and using the definition of polynomials being continuous everywhere. So we got another polynomial there for number 10. This is a nice, beautiful curve. And that function, the polynomial function, if I write it down here, is x cubed minus x plus 7. So this is that function f of x. We can write it as f of x. There we go. So we can evaluate this by simply doing some arithmetic. F of -2. So as x goes to -2, because polynomials are continuous, we just simply have to evaluate this using some arithmetic. Okay, plug this in. Now, be prepared on a test, ladies and gentlemen, to answer these questions without a calculator. Notice, I didn't need a calculator for any of these questions. We're just using arithmetic. I don't write tests that you need a calculator. So -2 to the 3rd power, because we're using order of operation. Please excuse my dear Aunt Sally. So we get a -8 minus a minus makes this plus. We get -8 plus 2 plus 7, which will give you -6 plus 7, and then that equals +1. I did not use a calculator. I'm deducing the answers. So the limit as x goes to -2 is 1 for this polynomial function. Let's look at this now over here. So we have -2 here, okay? As x goes, these x values again, approach -2 from the left, you are approaching, again, these points are going to a location, and then you can't see it so clear. I'm going to erase it, but approach -2 from the right. I want to go through these ideas. Again, these are x values. So on the curve, you're approaching the same location at -2. And it looks like we had to go all the way up here because what you're approaching is this point here. Okay, so every point on that curve here is an x and y coordinate value. So I want you guys to see this graphically. Alrighty, now let me get rid of what we're looking for. So we're looking for the address right in here. Okay, so it looks like x is -2, and notice this. Since this up here is 10, every dash mark is units of 2. 2, 4, 6, 8, 10. So halfway here, half of 2, 2, 4, 6, 8, 10. This is 1. So I just want to kind of really emphasize something that you want to take a look at there, okay? And it's not straight. See if we can straighten it out. Can we? Oh, no. Anyway. Looks like the left-handed limit and the right-handed limit are the same. They both equal 1 because you're approaching from both directions, if you remember. Oops. That's not it. You're approaching from here, from the left, and you're approaching for the right. Every x value has a corresponding y value. So you're meeting at the value -2, 1, and sure enough, that was the limit we talked about. So the graphical approach is verified. But I want to kind of warn you guys, remember, the essence really of this exercise is to recognize that you have a polynomial function and that all you got to do to evaluate a limit is what's called functional evaluation, meaning you're going to use eventually just order of operation for every polynomial, plug in the value, and use PEMDAS. And, you know, that's pretty simple to do. So like on a test, you might not even have a graph to look at. If you look at your homework questions in the book, there are graphs at all. But what I want to do as a lecture and as an exercise is kind of get you ready, I should say, for looking at both perspectives. We got to get a lot of experience here with that. So, all right. Thank you for your time.